Okay, we're finally at the spot where we're going to solve exponential equations. Remember, this is the reason we needed logarithm functions to begin with. So I'm going to start with an easy one, work to a lightly harder one, and then we'll do one of the examples that we started with. So example number 1, I just want to grab a marker that works and just say something nice and simple. I want to solve the exponential equation. How about just some things like 5 to the x equals 17. Now, by the way, I know that 5 to the first is 5. I know that 5 squared is 25, so I know x should be 1 point something. Meanwhile, what am I supposed to do? I need to get that x out of the exponent. And this is what we do. I need to take a logarithm on both sides. We usually use natural logarithm. So if I see an x in the exponent, I take logs of both sides. Especially if the x is all by itself on one side. We get something that looks like this. The ln of 5 to the x equals 17. The ln of 17. Now, what did that get me? Well, the third magical properties of logarithms says, if you have the logarithm of something to a power, you can bring down the power. So I'm going to get something that looks like this. I get x equals, no, not yet. One step ahead of myself. I get x times the ln of 5 equals the ln of 17, like that. Now, the ln of 5 is a number. It's like 1 point something. The ln of 17 is like 3 point something. I don't really care about that. All I see is a number times x equals a number. And I know how to solve those kinds of equations. I just divide by ln of 5. So I get x equals the ln of 17 divided by the ln of 5, like that. And we have solved the equation exactly. If I go graph 5 to the x and I go graph 17, I'll get a number. If I plug in ln of 17 over ln of 5 in my calculator, I'll get the exact same number. So that's our first example of finding the exact answer to an exponential equation. Let's make something a bit harder. We'll call this problem 2. And we don't have to make it nuts, but we should make it a little nuts. So I'm going to write down 5 times 11 to the x equals 7 times 2 to the 3x. We'll sometimes get ones that look that complicated. They're usually a little bit simpler. Now, in the last one, we said, hey, we see x's in the exponents. Let's take logarithms of both sides. You can do that, but it'll fill 2 boards like this just to finish. So when I see an equation like this and I'm thinking I want to use logarithms, a much better practice is to try to get all the x's on one side first. So what I want to do is divide both sides by 2 to the 3x and divide both sides by 5. So I'm going to divide both sides by 5, like that. I'm going to divide both sides by 2 to the 3x, like that. And what that will do, the 5 will go over here, the 2 to the 3x over it will go like this, and so I'm going to get 11 to the x over 2 to the 3x, like that. I'm going to give a big space here because I want to do this a little simplifying, like that. Now that's good. It looks much better, and if I started taking logarithms, I could do it, but it would still be a little weird. What I want to do is use our ordinary rules of exponents. We've already done some rewriting like this. What I want to do on the left-hand side is write the left-hand side as something to the x, and we're going to use our rules of exponents for this. So what I'm going to do, the top is, I can't do anything at the top, that's just simple. We've done this when we were doing compound interest problems. This is actually 2 cubed to the x, like that. Yes. Now I have 11 to the x on top. I have 2 cubed x on bottom. So what I really get here is I get the entire fraction 11, and 2 cubed is just 8. So I'm going to put 8 like that, and I get that. So we started out with a fairly complicated equation. We haven't solved anything yet, but now you can see I'm in exactly the same situation we were in the last problem. What I can do is I can now just take the natural logarithm of both sides. Go the ln of 11/8 to the x equals the natural logarithm of 7/5, like that. want to do? Well, we have that third magical properties of logarithms that says if you have a logarithm of something to a power, you can bring down the power. So what I'm going to do here is bring down the power. Now what does that give me? That gives me x times an icky constant equals another icky constant. But no matter how icky the constant is, we can actually just write down the answer. So I'm going to go like this. I'm dividing both sides by the ln of 11/8. So I get the ln of 7/5 divided by the ln of 11/8. Come on, make that look like an 11. And can we see that? Yes, we can. All right, so in order to solve this exponential equation, I got all the x's on one side, and then I had to rewrite it using my rules of exponents. So my rules of exponents had to be good as a single thing to the x. Once we could do that, we took the logarithm of both sides, we divided by the icky constant, and we're all done. Now, by the way, we could have solved this graphically just by graphing that side, graphing that side. That's two different exponential equations, functions, I'm sorry. They hit each other. We can use our calculator to actually find the answer. It's not so bad. All right, so meanwhile, what I'm going to do is I'm going to go to the first example we saw when we were trying to explain why we might need exponential functions to begin with. I think I can get there by doing this. All right, let's see here. Here's, wait, I want to go up just a little tiny bit. Can I go up a little tiny bit without this thing freaking out? Okay, we put $10,000 into an account that is compounded monthly at an annual percentage rate of 4.2%. We can retire when our account hits $1 million. When will that be? Well, we got an equation for the compound interest. We know we're supposed to hit $1 million. What we would have done last week, and really that's just as good as what we're doing now. We would just graph the left-hand side, we would graph the right-hand side and see where they cross. Meanwhile, what I'm going to do is take that equation that says 10,000, right? See, not that one. Markers. I have 10,000 times 1 plus 0.042 over 12. We'll fix it. 12t equals $1 million. All right, I'm going to switch over to the whiteboard so I can try to solve this the way we just did. Okay, so there's our equation. Now how do we do this? I don't want to just take logs of both sides because that 10,000 is going to be a mess. So what I'm going to do first is I'm going to divide both sides by 10,000. See, if I divide this side by 10,000, the 10,000 goes away. If I divide this side by 10,000, I'll see 4 zeros goes away here, 4 zeros go away here, and I get 100. So that's not so bad. So I'm going to get, let's see here, 1 plus 0.42 over 12 to the 12t equals 100. And that's the equation that we need to solve right now. Now, how am I going to do this? Let's see here. Well, I would like to do this exactly the same way I did before. What I want to do is rewrite the left-hand side as something to the t. This is something we were doing those compound interest formulas anyway, so it's not so bad. What I'm going to get, yes, I'm going to get 1 plus 0.42 over 12 to the 12 to the t equals 100, like that. So that's 1 plus 0.042 over 12 to the 12 to the t equals 100. What I want to do now is I want to take the natural logarithm of both sides. We're doing natural logarithm because it's the easiest one for a computer to calculate. I'm just going to write this out. I'm going to get the natural logarithm. Let's see here. ln like this. Good. Of the mess. Yes, so I get 1 plus 0.42 over 12 to the 12 to the t equals, taking the natural logarithm of the right-hand side, the ln of 100, like that. Okay, we're still just solving. Now, why did we do that? Because we have that third magical rule of logarithms, and you can see that's the one we're using more than anything else, that says if I have the ln of a constant to a power, I can bring down the power. So we're going to get t times the ln of the mass, 1 plus 0.042 over 12, parentheses, to the 12, like that, equals the ln of 100, like that. And what we want to do is just divide by this horrible constant. So I'm going to get t equals the ln of 100 divided by the ln of the icky constant. Ta-da! That's the exact answer. Now, to get an estimate, I have to put that in my calculator. But by the way, that's going to be more work than it would have done had we just graphed both sides. So graphing both sides very often gives us as good an answer as finding the exact answer first and using our calculator will. But meanwhile, we now know how to solve that kind of exponential function, exponential equation exactly.